Good morning, everyone. Thank you for having me here. I am interested in topics which people attending this program tend to step back and avoid touching on just to neglect. But anyways, I am a first-year fellow of this N3ES collaboration, where N3ES stands for Network for Neutrinos, Nuclear Astrophysics, and Symmetries. I decided to give a general talk on the interesting neutron star properties from point of view of gas matter, and will also briefly mention the exciting collaborations, exciting research activities among our collaboration network. It's not going to the next slide. Okay. Yes, so we observe neutron stars by detecting photons, neutrinos, and gravitational waves emitted from them. The good sources include mergers of neutron star, neutron black holes, and Quark-like supernova and their remnants, accreting stars, neutron stars, isolated neutron stars, magnetized gamma ray bursts and milliseconds pulsars, and also the extremely compact and stable double pulsar system. With the improvement in facilities and technology, we expect increasingly better constraint on the internal structure and composition of neutron stars. So LIGO is now being upgraded, and we have been expecting the science data from NASA. There will be new observational programs, such as laser interferometer space antenna and square kilometer array, and the Kuiper camera contact, which is a new neutrino detector planned at Japan. Okay, so we have the ground-breaking detection of massive pulsars, which impose stringent constraint on the theory of dense matter. And also in 2017, we have we've seen the first detection of gravitational waves from binary neutron stars. Other advances include the continued monitoring of temperature, thermal radiation from accreting and isolated neutron stars, which actually provide evidence the existence of neutron star tracks. And we have seen the extremely precise measurement of the change in spin rates of fast rotating pulsars that infer we need some superfluid component in their interiors, which we have discussed. Created in the aftermath of supernova, neutron stars exhibit extreme conditions that cannot be observed elsewhere. Of course, the neutron star has a typical mass 1.5 solar mass and radius about 12 kilometers, and its central density can be as high as 5 to 10 times saturation density of neutrons and protons observed in a laboratory. So these extreme conditions enable neutron stars to be excellent astrophysical laboratories for studying dense matter, and the studies will need connections to nuclear particle physics, astrophysics, general relativity, and atomic and condensed matter physics. So the global structure of neutron stars are mainly determined by the accretion state, which is the relation between energy density and pressure, while the dynamic properties, such as evolution of magnetic field, of their thermal and spin properties, are related to the material properties of dense matter. For example, the elasticity, viscosity, opacity, and superfluidity. So the mass radius relation is obtained for relativity stars by numerically solving the hydrostatic equilibrium equation. So for normal nuclear matter models, the radius of neutron star is relatively insensitive to the mass. So on this plot, these curves are representative of normal nuclear matter models. If we have large amounts of softening due to hadrons, they tend to give stars with much smaller radii and a smaller maximum mass. ruling out. They are ruled out by the observation of this having pulsar we have observed. Ideally, if we have simultaneous measurement of mass and radii, we can discriminate the equation state models we have proposed. But unfortunately, the radius estimates are hindered by uncertainties in, for example, distance measurements and composition of the atmosphere and interstellar absorption. So we have mass constraints so far, independent two of them. One is the maximum mass constraint. The other is the tidal deformability measurement from pre-merger gravitational wave signals. So these two constraints are able to put a limit on the so-called stiffness of the equational state. So stiffness is characterized by how fast the pressure rises with energy density. So equational states that are stiff typically give rise to larger neutron stars with higher maximum masses. But having massive pulsars detected, the soft equational states are ruled out. The tidal deformation, tidal deformability measurements inferred by LIGO disfavor stiff equational state. So this likely tension infer there is a rapid switching from soft equational state to stiff equational state. And there are also other interpretations if we have phase transitions into hyperonic matter, condensates, and quark matter, or if we have pure exotic straight quark matter. The stars are made of purely quarks and no normal neutron matter content within it. We have seen recent advances in both theory and experiment from the nuclear studies. So Will has just given a nice introduction of nuclear physics involved. So basically, in normal nuclear matter models, the stiffness parameters are the symmetry energy S and its slope L. And models giving higher values of these parameters tend to give a stiff equational state. And the calculations for asymmetric nuclear matter, we have seen the state-of-art calculation from Carey-Patrick field theory and quantum calculations, and they also indicate there is a rapid switch from soft to stiff US around high saturation density. Because of that essential distinction between symmetric nuclear matter we measure in nuclei, which consists of equal numbers of neutrons and protons, to the nearly purely neutron matter we anticipate in the neutron star is not a trivial extrapolation, of course. And we have experimental efforts to probe the subnuclear regime in the lab. So the speed of sound itself, the derivative of pressure with energy density, is a direct measure of the stiffness. And at asymptotically high densities, it approaches the conformal limit of 1/3, which is suggested by the perturbative QCD studies from below with increasing densities. However, if we want to support two solar mass neutron stars that is so heavy, we need speed of sound actually approaching the speed of light at several times saturation density, which is generic if we confine ourselves in the standard nuclear matter models. There are alternative scenarios if we have phase transition. If there is first solar phase transition, the phase boundary between hadron and quarks introduce an intrinsic softening, and then supported by stiff quark matter. Above that condition, we can still reach to solar mass. There is also a alternative scenario that with a crossover transition from hadron to quarks, so-called quark-ionic matter, there's a boost in speed of sound, and then naturally drops down and approach the QCD limit. At high temperatures, we anticipate the speed of sound to match that is QCD calculation and heavy ion data we see in experiments. So within this normal nuclear scenario, as Will just mentioned, we can do a simple mapping from the equational state to the tidal deformability and the radius of neutron stars. So this work last year combined low density and carrier factor field theory calculation with the high density extrapolation using polytropes. So on the left-hand side, and pressure versus energy density. And we see the straightforward correlation if the slope is too small. So represented by this band, it will give maximum mass smaller than 2 solar mass, and then rule out the equational state within that band. If the slope is too high, the red band tends to predict tidal deformability higher than the LIGO measurements. So these equational states are also ruled out. So there is a narrow range of this pressure versus energy density plane within the standard normal nuclear matter model to be compatible with the 2 best constraints we have so far. And they predict a lower bound on the lambda, the tidal deformability for 1.4 solar mass stars to be 224. Again, this is within normal standard scenario, no phase transitions. If we have strong phase transitions, possibly any exotic form, deconfined quarks can be there, hyperons can be there, and condense mesons. We don't know, but if there is some type of strong first order phase transition, the speed of sound behaves very differently, and introduce signatures such as mass increases with decrease in radius, but at some point when we approach the phase transition, there is a discontinuity that won't be observed in other non-phase transition case. There are a lot of theoretical models on studying this possible normal phases can be present in the core neutron stars, and we use this model-independent parameterization to constrain the phase transition parameters, where the phase transition occurs, and how strong is the phase transition, and how stiff the Quark matter after the transition can be. The evidence distinguishes for the strong case is, as I mentioned, discontinuity in the mass radius and the tidal deformability. So as I emphasized, we can see a signature, for example, on the mass radius curve in this phase diagram for phase transitions, where the onset density is and how strong that phase transition is, and the stiffness of quarks. We have, for example, the D type of mass radius. You can see for typical range of mass, there can exist 2 neutron stars with very different radii. So let me emphasize, this is the most distinguishable feature of phase transition in terms of global static quantities. Unlike the smooth phase transition or the crossover case, where basically the exotic matter resembles the normal nuclear matter, and one cannot distinguish them from the normal heterogeneity model case, which is the masquerade problem for the detecting or inferring exotic matter from measuring global quantities. And again, we impose 2 constraints from observation, and the gray area is already excluded by the 2 solar mass constraint. It is actually a considerable parameter space. I plot only transition density up to 3 times saturation density, and higher densities tend to be ruled out. And also the tidal deformability for the hybrid stars generally are smaller than the normal nuclear matter stars. So the contours of 1.4 hybrid stars are what we plotted are all below the 800 value.
Can I turn you back to the previous slide?
Yes.
Yeah. So if I look at this, the long plot,
yes,
you have energy density for nuclear matter, energy density for quark matter, and you assume that you have a sharp transition from one to the other.
Yes.
It will look to me probably to be more reasonable to look at the maximum construction at that point and have a mixed phase
yes.
in between.
Exactly.
So you're discussing that?
That's what that is.
You're all right. No, I
yes.
missed that. Oh, sorry.
Yes. 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 Due to the uncertainty in the surface tension between the quark matter and hadronic matter, we don't know the nature of phase transition. Even if it's first order, whether we have quark hadron mixed phase development or just a sharp interface between the two uniform liquid matter. Yes, exactly.
What would be the condition to have a sharp interface?
The surface tension to be high enough, such that the separation of two uniform phase is energetically favored than to have mixed phase. It's similar to the pasta, right? Pasta phase. Why we have pasta? Because the interface, the surface tension is lower enough. But we have.
So what do you know about surface tension?
We don't know. We don't know.
So for that reason, you discuss various scenarios or not?
So actually it's work in progress for the mixed phase case. So we first look for conditions of maximum projection because it leads to the most distinguishable signatures observationally. The mixed phase is going to be smoothed out a bit. The effect, for example, the discontinuity in mass radius plot in the tight mobility near the phase transition, that discontinuity will be smaller. But to what extent depends on how the mixed phase is constructed. The best distinguishability is from the maximum construction of sharp phase transitions. In even milder case, for example, in the Papriani model that is characteristic of second order phase transition, a crossover, the
I wasn't aware of this paper and I looked at it.
Which paper? This one?
Yeah. And I should have been my colleagues, but I wasn't aware of it. Then I looked at the energy density and functional density.
Yes.
Completely different profile than the one you draw.
Exactly.
Because it's like this and like that. And I don't see a second order phase transition, but I see a maximum construction. Clearly, it's
no. Second order phase transition is in this case. For this crossover scenario, the second order phase transition with a smooth crossover. So you don't see any discontinuity in their paper for the energy density versus pressure, which is different from our discussion that there is a sharp discontinuity in energy density when the first quarks appear.
So which scenario should I believe more? This one, that one?
At least all of them, because I don't know which one to believe. And we want to see observationally how best we can rule out or ruling anyone. Yeah, they are different.
What arguments you can bring in favor of one or the other?
No. There is no favor in my point of view. We have possibilities. It's just so uncertain. Uncertain about exotic scenarios. I'm not saying this one we present is the best or it's the true case in nature, but we have alternative scenarios and we are anxiously waiting for solutions to rule out or rule in.
So what do you need in order to resolve this? What kind of new information? I don't know, not experimental, but it could be theoretical, it could be some kind of information to decide which one is more reasonable.
Yes, that's why I mentioned the evidence signatures.
Well, that would be experimental.
Yeah.
Right, observational.
So
what would be from theoretical point of view? What you need to know more about one or the other matter?
Wait, so there are so many theoretical models for Quark models, and
right, they have deficiencies. So for that reason,
yes.
Which one you have to improve? It's closer to reality than the others.
The problem is there is no reliable way to extract Quark models down to densities that relevant for neutron star cores. At ultra high density, we can trust predictability calculations.
Start writing science fiction at that point. You see, that would be equally good, right? So that's not an argument for a scientific journal. So I'd like something you see more tangible, you see, which I can talk, you see, not simply throwing a video. Okay.
The ideas are not thrown in. It's based on the inadequacy of theory models. It's not we start with throwing such ideas. It's because the deficiency of theory, exactly as you mentioned. That's the reason we are eagerly waiting for observations to help us, to help theory.
Yeah,
there is no fundamental
point, it could be confirmation bias. oh, we saw that, so therefore this is better. That doesn't mean it's one
Yeah, there's no.
Then the other is better than the
No,
other
there's
because you
of
saw
course.
something.
Yes,
Right?
yes,
So
there
I
are
think-
different scenarios based on all various assumptions, and there is no solid argument saying this is the fundamental theory that describes neutron star equation state.
May I also ask a little bit? So evidence signatures, probably I missed it, but what would be examples for evidence signatures? So signatures, so how?
Yeah.
This
So,
is all the way to discuss.
yes, exactly. So one evidence signature is on the mass radius diagram. Normally, for neutron star models with hadronic matter, mass radius would look like continuous smooth function like this. And observationally, we should have a detection of multiple data points, right? And the map of this curve and inverse engineering tell us the energy density versus pressure. But we have only one not data point here, it's just horizontal line. And signature for the strong phase dilation scenario would be something like the V type of mass radius. If we observe one star on the green curve, which is purely hadronic star, because the central density is below phase dilation, and one on the red curve, which is above the phase dilation point and is a hybrid star. These two stars can have the same mass, but very different radii, which will never be realized in normal case. That will be an evidence figure. But if we don't see it, we cannot rule out this scenario because we don't have enough data.
Right.
That's my one example.
So basically, you're looking for radii which are smaller than what
Yes.
And this quite clearly or almost clearly then approaches your understanding what kind of the scenario is. For instance, of those that you have suggested. So your scenario, for instance, Larry's scenario or other scenarios. These are basically very different.
Yes,
below
this
those
is the distinction. Yes,
Okay, this is the distinction.
this is the distinction. So if you check their paper when they plot the mass radius, actually they have a slightly hint in the radius, and for a transition density, they have a slightly larger radius and then goes to the stability, but still it's a smooth continuous function.
Right.
That's why I said of evidence signature.
Where does there is this one data point. So where does that sit on this plot? That was the neutron star merger, right? Did they get a?
Interesting. I get to that, but the constraint of on radii, they extracted from teledeformability, neglect all possibility with phase transition. So that range you can only believe for normal nuclear matter models. Yes, that's the limitation, and we want to expand that data analysis by including phase transitions. That range of radii will be different. We don't know yet.
Now, if we go back to the previous one, and you see even think of Quark matter, one can hope to get some information from lattice QCD calculations.
That's
So
right.
what's needed, what's people haven't done, what do they have to do in order to get this? Some information should be useful for you. You can discuss not theoretical models, you see, but ask them, you see, we need this type of.
Exactly. We need them to give us finite chemical potential calculation, but not possible
But
yet.
you can put that in the list. We need exactly this, see, and then maybe somebody will do this type of calculation. Because there are many groups.
I don't think they don't want to, but
Solve the sign problem.
yeah, limited by
So the
the
same problem is you got lots of needs all the time.
Yeah.
But the things, the question is, you can go and find close.
Yes.
Well, yeah, as soon as they can, they will. No, there is no answer.
No,
As soon as they can, they will, but no one can. No one knows that.
maybe they're not interested in this problem.
Oh, they're very.
Of course they are.
They're very interested.
Yeah.
The community behind that
So this,
exactly this direction.
yeah. So this temperature axis is what can be probed by lattice QCD and heavy-ionic collisions, and neutron stars along on the horizontal axis, and the relevant densities for neutron stars are far up the ridge of the other
And you
two
need the
regions.
low temperature, right? You need the
Exactly.
low temperature.
Exactly.
As far as I know, you see there, you see, can go at low temperature, high density.
Exactly.
You know, asymptotic freedom, so you can go from there and construct something. You can go from the other side.
Yeah, that is the
That's very part of
that
it.
is the asymptotic high density regime, but still, for example, about 50 times saturation density. Neutron star can reach maximally 10 times saturation density. So there's a huge gap that we can only extract information from observation. Theory is hopeless.
Can I say something about this? I mean, it looks to me that since you are interested basically about thermodynamics, right? So it's a question of state and phase transitions. So it seems to me that the problem is to have a particular scale where you're interested in correct effective QCD. So because QCD is basically something that you cannot expect to solve at a range of scales from first principles. So you need, at this point where you have a question, you need an effective theory that it is true to the QCD principles. And because it is a strong interaction before.
Yeah, the limitation for effective field theory is they cannot do beyond high saturation density as Will just brought. Yeah, but yes, exactly. Actually, this is not going to be my main point. I want to talk about cooling that constrains superfluidity that will be useful or interesting for you guys. Yes.
But I just make one more comment. I mean, they're actually just. I mean, as you said, the general rule is to go from the high chemical potential side using perturbation theory, and going from the low chemical potential side using theory and other things like that, and then to try to meet at some point what you show. And this is one way of doing that using
Polytropic
approximation, but there are also other ways. So there are actually a couple of groups at the moment trying to understand, so using the data points from gravitational waves, for instance, and from others, and trying to understand what is actually the equation of state in between, or to make it smaller, smoother, and so on.
So the LIGO group, they essentially use this polytropic extrapolation themselves. Yeah.
Right, but apart from the LIGO group, there are also basic QCD groups that, for instance, the Kurkula and
I think this is
like that. Sorry, this is that.
Yes,
exactly the same thing.
Apart from those, there are also others. Sorry, this is from them. I thought it's from the. But there are also other groups that have, for instance, a slightly different approach. They what they have is like equation of state parameterized in a different way.
Oh, the spectral decomposition, right?
For instance, So there are like several groups trying to get these bands as narrow as they can, but and so on.
The important thing is all they rely on parameterization.
Yes.
This is the essential point.
Yeah, or to get the parameterization as general as possible in order to minimize basically the parameterization itself. Because they are like broader error bands.
Yeah, to broadly represent some sort of realistic models.
So basically, my comment was only to say that
yes,
this is
I completely agree with you.
A big issue. Yes.
Yes.
To add to that. Sorry, I didn't. Sorry. Yeah.
Let me go quickly to this. Okay, so this is other signatures that might be useful to discriminate exotic matter. Okay, so there are these EoS executive universal relations involving the moment of inertia. For example, it has been shown that on the plot, upper left plot, the deformability versus moment of inertia correlation is found to be accurate within 1% for normal nuclear matter models and even self-constrained stars. But if we have sequential phase transitions like this type, two phase transitions from first order, transitioning into different types of Quark matter, it can actually deviate from this universal relation by 9% under certain combinational parameter space. The other universal relation relating compactness, which is the ratio of mass versus radius, and the moment of inertia is also very accurately obeyed by all these types of equational states. But if we have pure dark matter stars, there can be significant differences. And of course, we cannot measure moment inertia right now. In the future, in the next decade, probably we can have the observation and rule out the exotic phases or rule in some very mysterious sequential phase transition. So in summary, I want to say it's probably very, very difficult for measuring the bulk properties to detect or infer exotic matter. What we need and what are more promising is going to be the dynamic properties like cooling and spin evolution and other stuff. So that's why we want to study the thermal emission from neutron stars. Basically, we have two scenarios of standard cooling and enhanced cooling. The most efficient neutrino emissivity emission mechanism is from the direct workout processes, but it has onset density threshold to operate, which means we need neutron stars to be heavy enough to cool down very fast, and then they look very cold in this normal scenario. Superfluidity, when they are present, they can quench the workout processes, but introduce this additional pair breaking formation mechanism that has been discussed already. The extreme cold sources are very important because we need them to reveal whether fast cooling are present in massive neutron stars or not. For very hot stars, they are good candidates to limit poorly understood mechanism. For example, the likely heating, likely cooling induced by axion coupling to neutrons. So in the standard nuclear matter, the only possible fast neutrino emission is direct workup. It requires density threshold and also can be easily suppressed when superfluid becomes present. But if we have exotic matter, there are additional multiple direct workup channels which relieve the neutron star of being the requirement of being very massive to cool down fast and appear cold. So since superfluid can quench workout processes, both fast one and slow one, and then trigger the medium cooling by the pair breaking formation, ideally we can constrain superfluid from cooling observations because it regulates the cooling track of isolating neutron stars and the thermal balance of accreting neutron stars. So the neutron triplet pairing is believed to be confined in the crust region and with critical temperatures much higher than the neutron star internal temperatures. Therefore, we do not expect cooling to constrain this gap. The other two pairing gaps, the proton singlet and neutron triplet, can penetrate deep into the core. However, the magnitude and the density dependence of these gaps are fully known. Therefore, we can use cooling data to constrain these two types of gaps. If we assume a Gaussian shape of pairing gaps, we can do feeding between the output luminosity data from cooling simulation to the observed data point from luminosity. Actually, we ignore exotic matter for now and do such fitting to two different systems. One is quiescent transient with accreting neutron stars. We observe the luminosity when they are not in outburst stage. And also there are 13, I guess, data point for the isolated cooling neutron stars. We fit the luminosity and age to the average estimated value of these stars. So immediately we see inconsistency, and also the results are highly sensitive to cold sources. To explain the coldest one of this quiescent transient, we need the proton gas to be even lower than 10 to the 8 Kelvin, which is just very crazy. You need direct workup not to be suppressed by protons gap to explain that single source. But for isolated neutron stars, for example, to explain the relatively low temperature of Bella Pulsar at its age, we need actually proton singlet and neutron triplet to be relatively large, so that the pair breaking formation mechanism of neutrino emission can be maximized at pertinent temperatures. So this discrepancy between fitting with two different systems actually seems to necessitate we cannot ignore exotic matter. For example, hadrons can play an important role. Even if they can solve the equation of state, but if we have a slight amount of them, it can contribute significantly to the fast cooling mechanism. So this is kind of the conservative approach. We need something exotic because currently we are unable to explain the discrepancy. Yeah, so there are other dynamics involved. For example, in supernova, probably neutrinos play a crucial role. They are trapped. They are trapped during the collapse stage, but then revived the shock wave, assisted by rotation, convection, and magnetic field. So we have observed the supernova 9787A with the detection of neutrinos, and they escape actually on the time scale, diffusion time scale, 10 seconds. Yes, useful observation. And also we anticipate in the explosive environments, such as the neutrino-driven wind in collapse supernova or the dynamic ejecta, the rapid neutron capture on seed nuclei, the R process, will produce the heavy elements beyond the number of iron, the ground state of matter. So to study all this, to actually have just some idea how microphysics can affect, for example, the gravitational wave signal, the neutrino spectra, the ejecta component, and the amount, we need actually several improvements. First, we need improved calculation of equation state and the neutrino matter reaction rates. And also we need the improvement in the code for hydrodynamics, numerical relativity, better modeling of mergers and supernova. And last, we need a proper treatment of neutrino flavor transformation, which can play a crucial role in the supernova explosion and detection. So all these are within the research activities at the network. Yes.
So the question, I mean, you look at physics of dark matter, and then there's this error of lattice QCD and then the theory tightness. So first of all, why is lattice QCD any way connected to dark matter, or how is it? I mean, we just don't know what it is, right? Why is the interconnection between them any way to lattice QCD?
It's probably the different regimes on the phase diagram. They are not. I don't think this arrow means they are directly connected, but
I think there's one connection where the scattering of dark matter with nuclei is related to form factors, and those form factors can be computed on the matrix. So that is one
So
connection.
in that sense, it's not like actually performing computations of dark matter, it's basically of the interaction with some form.
No, yeah.
Okay.
Well, there is a proposal that dark matter might be spectral parts. You can ask me about that later if you want.
But there are many proposals what dark matter might be, right?
Yes, there are lots of other proposals.
Yes. Okay. Sorry.
thank you for the clarification.
So when you say nuclear physics with dark matter, interaction with dark matter, I think the title is a bit. Okay. So
Yeah. For example, the coupling between dark matter candidates with neutrons. Yes. Yes. And these, so these are the focuses of the research activities within our network, rely on collaborations. And we have being upgraded, and some newly built detectors will come online, and we anticipate multiple merger events to be detected and statistically studied of equation of state can be constrained. For example, this phase transition scenario can be ruled out completely, or it's still a possible scenario. And of course, if we have continuous gravitational wave sources, that will help us extract information on deformations of neutron stars and possible oscillation modes. So I just wrap up the topics related to dense matter in neutron stars, and I highlighted the observability of exotic matter from both the static side and the dynamic side. Of course, we need detailed study for the system if observationally we saw a signature, or we see a signature of such phase transition. For example, the nice estimate about superfluid vortices and flux fields in the core region will become invalid if there's strong phase transition to quarks, and the component, the superfluid component with quarks, should be investigated instead. And there are related questions and efforts from theory on the nuclear side, especially the manifold theory of strong interacting systems that still limited by this cutoff at 5 separation density. And dynamic response, we don't understand actually how neutrino and neutron nuclear matter interacted. That will change the modeling of supernova and merger and experiment. We have, for example, the high resolution measurement of neutron spin, right? And also the neutron rich nuclei to be created at upright facility for rare isotope beams, and also heavy ion collision will probe the other directions on the phase diagram, might have some implication for the full theory that can be developed. Okay, so I will stop here and happy to take questions. Thank you. Yes.
Which one you want?
So 1 through.
Okay.
Okay. So for the how many sources, quiescent cooling sources went into that plot on the right?
So on this plot, we actually fit only to the hottest and coldest stars, 2 data points. But actually, we have about, I don't remember the exact number, 14 or 11. The data of their quiescent luminosities, yeah, on the accretion rate versus luminosity plane.
Okay.
Yes.
And you said that it's overly sensitive to the cold.
Yeah, to the coldest one. Yeah.
Do you if you assume that, say, it has a partially accreted crust, would that change?
No, not actually, because the crust is going to affect the surface tension. Surface luminosity relation with the internal temperature relation.
Yeah.
If crust is partially accreted, the inferred internal temperature is not going to be higher than the current limit. It's the data point is already an upper limit.
Right.
Yeah. So that is going to, not going to change big for the implementation for the gap models.
Okay.
You mentioned that the good signature would be to observe 2 types of neutron stars. You see, you had that plot, you see different radii, same mass but different radii, correct? That one.
There are not
the
2 types.
Curve, right?
There are not 2 types. They are just 2 different central density.
Yeah. No.
Yeah.
That's what I meant.
Yeah. Yes.
Now the question is, you see, the existence of one or the other, or both of them, depends on the equation of states and how many branches you might have. You have normal equation of state, magnetic, exotic, quark, whatever. And you might ask the following question: can you form those in a supernova collapse? because people have little information about the equation of state at high density, and for that reason they can fit into the codes one equation of state and the other equation of state and find out, you see, if there is a dynamical way to reach one or the other, you see, in this way. So I think that will be an interesting, you see, way to proceed. You see, can we reach dynamically this or that?
There's only one paper, I guess, by the and with the code from the Oak Ridge National Lab, they did a supernova explosion with the first order phase transition, which create a second neutrino signal after the collapse.
So that points to the fact that it could be two different radii.
That is only after the stars are cold enough, right? We can detect the cold neutron stars on the two separate branches. For supernova, we don't know where the remnant neutron stars reside on different sides.
You see,
So I think Oral's question is, with that equation of state, can they form neutron stars in both branches or only one?
Oh, that depends. Yeah, it depends on the
Yes,
production mechanism and the progenitor mass of
I'm
neutron.
sorry?
The progenitor mass of the supernova.
But you can reach both branches?
Yeah, if they
with the right
they result in different central densities of that neutron star.
No, I want to see from the supernova, you see, collapse can end up in either one, that place or this place. Under what conditions?
Yeah, the paper I mentioned, they result in a hybrid star on the red branch.
But they don't have both. This is what I'm saying.
You cannot have both stars
No,
in one.
because if both are possible.
Yeah, that's true.
Claim.
That's true.
There should be a way. You see, I start from this initial condition, I end up here. Start from this initial condition, I end up there.
That's true. That's why.
Is there such a study?
No, definitely not.
That's what I'm asking.
But I think it's pretty easy to produce them on the one branch.
So the question was,
but it's not the same. You can do the second one.
Well, that's what they showed.
That's the paper. That's that paper I mentioned. They showed the neutron star with the Quark core created after supernova, right on the red branch.
And I think you can take other work and say yes, and you can create them on the other branch because that's not so hard.
That's easier than the.
I guess they could with that do what you're suggesting. Just they were interested in having high enough densities to feed the second neutrino signal from getting.
No, but if this is important, you see, to figure this out, you see, what the things. What's the probability to have this type of neutron stars or that type of neutron star?
It just depends very strongly on what you put in, because you put in this jump.
Because the theory is so bad, it is so fine. At least you'll try this.
How many supernova simulations are there?
Is important, right?
Like different kinds.
Because these are pretty expensive, right?
I don't know how many they do.
Well,
10, 100,
I'm
1,000.
not sure. They even have problem with the 3D explosions.
Yeah.
Currently, can only do 2D more relatively successful.
Do I remember correctly that they claim that the phase transition helps them get the explosion in that way?
I don't remember. It's paper in 2008, I guess, more than 10 years ago. No?
The one I was thinking of more recent.
Oh, more recent? Maybe I didn't
There's
check.
some more, but it's the same people, so I think.
Yeah, the same group using the same equation of state models. But that, I guess, is the only example for simulation of supernova. Yeah, in the context of strong phase transition.
Can I ask you a slightly different matter? A long time ago, when I was still a young man, I got involved in some relativity calculation of neutron star collisions. It was related to light because they wanted to know what type of gravitational waves we expect. What I would like to ask you is that based on the viscosity values that you actually have, what type of dynamics do you expect during these collisions? Should it be irregular or should it actually be open collisions?
You mean in general for neutron star mergers or particular for phase transition?
What it was about was basically two neutron stars spiraling.
I don't think the current numerical simulation actually takes into account viscosity to that level
So you think that they are without any viscosity?
They are lacking input.
But it's highly turbulent in the
Yeah.
way.
Well, they've got enormous numerical viscosity. Overwhelm any real physical viscosity. So,
Certainly don't have the resolution to really resolve anything sensibly. Well,
so the resolution is the best resolution is today at 60 to 80 meters.
But based on actual viscosity values and perhaps other parameters, what type of dynamics would you expect?
Massively good.
What's the turbulent? That's what I would do.
Okay, any other questions? All right, thank you very much.
Thank you.